Hello everybody and welcome. My name is Huzaifa Siddiqui and this is a final project presentation for ADTA 5560 recurrent neural networks. Now, this project deals with time series data and training and building recurrent neural networks to learn about the information captured within time series. Now, what is an RNN or a recurrent neural network? Well, RNNs are powerful artificial intelligence algorithms that bolster the AI's ability to sort of learn by itself by approximating the human brain's neural architecture. The recurrent aspect of the neural network refers to how the same process or function is repeated time and time again over multiple either instances or cells or steps, each containing multiple neurons, which have built-in functions which update either weights, biases, or use gates to allow for learning during the process. And we'll cover a bit more about how that works in part 3 specifically when we look at long short-term memory cells. In this project, we assess both simple RNNs as well as, like I just mentioned, long short-term memory neural networks, or LSTMs, which specifically the latter of which boosts an RNN's ability to remember information over time. Now, as a brief roadmap, in part 1, I'll introduce to you a publicly available and acquired time series dataset, as well as talk to you about some of the data contained within, how much data, what kind of time series it is, and sort of a brief overview of the time structure. In part 2, we'll look at a simple RNN trained on generated sine wave data. We'll go through how I built that model, trained it, how the model performed during training, during validation and testing. And then we'll cover LSTMs. We'll cover the core concepts of LSTM cells, which are specifically the cell state and gates, and we'll compare it to simple RNNs. Then we'll utilize what we've just learned by looking at how I trained a first LSTM network on time series data. And then in part 5, we'll redesign that LSTM network and train it on the same data to hopefully improve the model's performance. In part 6, we'll compare how the two models performed, and in part 7, I'll conclude with a project report with some conclusions and some learnings of what I have gained from this project. So let's move to part 1 first, a time series dataset. The time series data set that I used was sourced from the University of California, Irvine, or UCI. The UCI's machine learning repository. This data set comprised 9,358 records and 15 attributes. It was named Air Quality, and it contains hourly data from March 10th, 2004 to April 4th, 2005, and the download link you can see on your screen. That is where you can acquire this data set should you be so inclined. Now, the data is collected from an air quality chemical multi-sensor device in some undisclosed Italian city, and the specific attributes of that data set you can see here on your screen. It includes some values from reference analyzers, such as the COGT, which is a true hourly average concentration of carbon monoxide, as well as some values directly from the sensor response, such as the titania hourly average sensor response, tungsten oxide hourly average sensor response, as well as temperature, relative humidity, and absolute humidity in that city during that time frame. Now, as we move then to part 2, we see simple RNNs on generated sine wave data. Now, the sine wave data that I generated comprised of 2,048 data points, and I trained a simple RNN network that contained 256 neurons on this data. Now, the architecture of this RNN was fairly basic, with only 2 layers. The first layer having these 256 neurons, and the very second layer being the output fully connected dense layer consisting of a singular neuron. There's a very brief overview, a very rudimentary diagram of the neural network you can now see on your screen here. This represents the simple RNN single layer where we have some inputs, weights, and biases that then feed into the neurons. There's a sigmoid activation function here. That information is then passed on to this feed-forward neural network, which is the fully connected dense layer. And that this circle right here represents the output neuron. Now, The way I generated that sine wave data was in Python, and as I prepared the model for training, I determined that I only needed 3 epochs for training. Now the loss of that model training is visualized here. The loss is in MSE, or mean squared error, because this is continuous data. And the reason I chose only 3 epochs is that over 3 or 4 iterations, I realized that even increasing the epochs to 10 did not actually decrease the loss that I saw in the training data. In fact, after 3 epochs, it spikes and then it never quite resumes or returns to this low point. Now, perhaps that was a mistake, because having too low of a loss value on training data could signal some overfitting. But nonetheless, I chose 3 for this reason, and for, if I'm being honest, some more expedient training. And I wanted to see what insights I might gain from this sort of limited model training. In my mind, I was potentially decreasing the model's complexity. Now, after the model was trained, I compared it on the test subset, or which here acted as the validation subset, and I utilized a for loop to generate predictions over this validation set. And there's the detail code for it is within a Jupyter notebook, but it's not relevant for our purposes here. What's relevant is that after those predictions were generated, they were added to the same data frame that contained the actual test data, the actual validation data, and they were compared side by side on the same plot. That plot you can see on your screen now. The blue wave is the actual sine values, the actual data, and the green one is the predicted sine value. Now, as you can see, the model does not perform particularly well. First and foremost, it doesn't really truly approximate the shape of the sine wave. You see here a sharp drop followed by a steep incline and a sort of plateau, another sharp drop, a steep incline, a plateau, a sharp drop, so on and so forth. What is encouraging, of course, is that the model has learned that there is a repetitive pattern in the data, as there is with any sine wave, a given amplitude and frequency within which it operates. So this model does try to do that. It does include, save for this first value, which seems to be higher than the rest of the trough here, all the peaks and troughs after that seem to be at the very same point, and there's a repeated pattern. So that's encouraging, but what's discouraging is how far off it is from the actual shape, and furthermore, the model wasn't able to learn that sine waves only have data within the range of 1 to -1. And this model predicted data below -1 here, even going so far as to almost be at -2, or perhaps this is -1.85, and going above 1 here, going up to about 1.1, 1.15. So the model doesn't do a great job, but it does loosely approximate a wave structure. So there is some encouraging aspect there. Perhaps some fine-tuning is in order to increase how the model performs. Regardless, let's now continue to part 3 and consider LSTM cells, or long short-term memory cells, and the core concepts of both cell states and gates. And we have to first consider, why do we even need LSTM cells? And that's because of the problem of the vanishing gradient, which refers to a phenomenon wherein, as a result of backpropagation through time, simple RNN cells, or simple RNNs, have an error value that becomes updated through this backpropagation, but that error becomes so small that the error value is no longer updated. And that then means that the machine, the algorithm, or the network ceases learning. And that's the end of that. And that's not what we're trying to achieve. Obviously, we're trying to achieve continuous learning, updated learning, and LSTM cells are able to counteract this by maintaining and preserving a more constant error rate during this backpropagation. The way they do that is because, first and foremost, cell states don't have any weights involved. Now, in simple RNNs, what we have is these weights and biases that are applied to the hidden state values. Those then update and change and modulate how much information is being kept through the process of a sequence, and that then in the backpropagation through time affects how the error value is updated. Now, cell states, because they don't have any weight involved, allow for information to be preserved through the sequence from start to finish, because it allows information to be preserved if it's deemed relevant or good or significant. The way that determination is made is through the usage of gates, and we'll cover that momentarily. But the key concept is that cell states allow information to flow from the start through to the end of a sequence. So in that way, cell states act in some ways as an information transportation mechanism or channel. You see here on your screen a brief diagram of what the LSTM cells look like. This is one LSTM cell. This part here, CT-1, references the previous cell, or the time step just before this. That cell's output becomes this current cell's input, which is then filtered through these gates and these activation functions, and provides the current cell state, which becomes the output of this cell state, which is then the input of the next cell state, and so on and so forth. And this straight line mechanism, the reason this straight line is here is to demonstrate that this allows for a direct flow through of information that's uninterrupted, only insofar as the information is deemed relevant. Now we keep talking about relevance of information, and the way that information is determined to be relevant is through these three gates within each cell which regulate information. We have the forget gate, the input gate, and the output gate. The forget gate determines what information from the previous cell state to keep or to remove. And the way that it does that is it utilizes a remember vector, which outputs a value between 0 and 1. If the value is 1, the information is deemed entirely relevant and 100% of it is kept. If it's 0, it's deemed entirely irrelevant and 100% of it is removed, or 0% is kept, and the range therein. In computing this remember vector, the way that this cell state here, pictured here again for your reference, the way it does this is, here's a close-up of the forget gate. It takes the two inputs. It takes the hidden state of the previous time step and the input value, the X input value of the current time step, and filters it through this sigmoid activation function. It then determines the hidden vector, shown here as ft, the remember vector, shown here as ft, which becomes the output of the forget gate, and also becomes the input of the very next input gate. Now the input gate determines what information from the inputs, the ones just referenced, the hidden state of the previous time step and the input or X value of the current time step, what information from those inputs should be retained for the current cell step. And before I move on, let me just quickly mention that the forget gate, importantly what it does is it uses the output of the remember vector to update the previous cell state. So whatever information comes in from the previous cell CT-1, the remember vector updates that information and determines how much of that should be kept. Now again, this input gate uses the information from the inputs. The input gate produces a save vector as its output. Again, we see here a picture, and here's a closer look at the input gate. It takes those two inputs, filters them through a sigmoid function, and produces this intermediary variable, the IT, which is part of the save vector. It also filters those through the tanh function. Now the tanh function produces values between -1 and 1. Those outputs become this, what you see here on your screen on the left and here on the right. It's a temporary current cell state value. Those two then provide the save vector value, which is the output of the input gate. It also functions as the input of the output gate, which is the very next gate in the flow. That output gate determines what information should make the new hidden state of the cell, of the current cell, which also then becomes the input of the very next cell. And because we have this sort of flow of previous cell state information flowing through, being filtered, and at the end of the cell, information of the next cell's hidden state being provided, we have that flow through of information that's preserved from one cell to the next within the neural network. And the way the output gate does it is it creates and processes a focus vector as its output, Once again, we see the cell state. We see the cell here on your screen. And this is a closer look at the output gate. Now that is here again. It takes those inputs of the previous state and the current state input, filters them through here as sigmoid function, and then it updates the current cell state by processing it through a tan-h function. That becomes then the tan-h, sort of the tan-h temporary CT value. Those two values, we see here on your screen, we have the FT, the remember vector, is added to the output here, the save vector, and then after filtration, those are all multiplied at the very end to produce the new the focus vector, or the new hidden state of the cell, the HT value of this cell. And in this way, the cells remember information because there's no weights involved, and the gates allow for the regulation of that information to determine how much of the information should be remembered, how much should be forgotten, and this is the mechanism they use to determine that. Now, of course, we have a look at LSTM cell states versus simple RNN hidden states. Now, there are some similarities and some key differences. Now, LSTM cell states also contain hidden states, as we just mentioned. But there are no weights involved anywhere within the cell state. In comparison, simple RNNs, the hidden state of a simple RNN represents the network's memory, and it does have weights applied to it, both in input and output, which leads to this potential problem where we have the information being lost by the time you reach the end of a sequence. Because cell states don't have that issue, they are able to preserve information, but simple RNNs have the potential to lose information. But most importantly, or perhaps not most importantly, but also what is of importance is that an LSTM cell's hidden state is not provided by weights. It doesn't have any weights applied to it, but rather, as just mentioned earlier, it's provided by the output gate. And those are the differences between the LSTM cell state and an RNN's hidden state. Now that we've taken a look at LSTMs and we've covered some of the core concepts, let's look in part 4 at applying an LSTM network to some time series data. Now, the time series data is taken from the same air quality data set referenced earlier, but this time processed to include only the temperature attribute. Now, notably, the temperature attribute had about 336 missing values from it. Rather than impute those values or perform any sort of imputation, I elected to drop and remove those records. Now that is potentially risky because I do run the risk of losing some of the structure inherent in the data. But what I didn't want to do was perform an imputation that would increase added noise and not be an accurate imputation method or an accurate enough imputation method, because there are some complex ways to impute, especially on time series data, but the coding for that is, I believe, beyond the scope of this course and is certainly beyond my current skill set, though hopefully not for long. Nonetheless, I chose to drop those values just for easier time series analysis. The core parameters that I chose for my LSTM network here, I divvied up my data into training data. 80% of it was training data. I reserved 10% for validation of the model, and I reserved 10% for forecasting on quote-unquote unknown data, but I preserved that data as a sort of test data set to allow myself to evaluate and assess the forecast data. Now the LSTM that I chose comprised of 4 layers. Each of those layers had 100 neurons, and between each of those first 3 layers there were 3 dropout layers. There was 1 dropout layer between each. The dropout layers had a dropout percentage of 20%, and the length of time series input was 113. I chose that. I chose 113 because it allowed me to arrive at a nice round 118 batch size for training rather than a decimal value in between. And I chose 10 epochs for training. Now we'll look here at a brief diagram of the neural network and this LSTM. Like I mentioned, we have 1, 2, 3, and 4 LSTMs, each with 100 neurons, and we have those 1, 2, 3 dropout layers between the first, second, between 1 and 2, between 2 and 3, and between 3 and 4. And notably, LSTMs 1, 2, and 3, they return their input sequences back to this LSTM, back to this dropout layer, back to this LSTM, because they're going to rerun the whole process. Now, the information in this network flows from left to right. Input is fed into this LSTM1, processed through. There's this 20% of the data goes to this dropout layer at the 20% dropout rate. Some of it's dropped. That input sequence is then again returned to LSTM2. Again, there's a dropout, and so on and so forth. To input to LSTM3, again dropped out. Finally, LSTM4 doesn't return the input sequence, but rather it processes the data and provides an output to the dense layer, fully connected dense layer, which provides the final output of the model. Now, that LSTM was built with the parameters mentioned earlier and trained for 10 epochs. The model's performance we can see here in this model loss visualization. Again, the loss was in MSE because we're dealing with continuous data. And on your right hand side, what you can see is the model's performance after I generated the same input length sequence, this time with a batch size of only 1 on the validation model to allow myself to evaluate it. Now, in between these two steps, there was some data processing done, some normalization and scaling of data, some assigning to data frames, but nonetheless, the generated predictions of the model, of this model that was trained here, you can see here in red, overlaid over the actual validation data. So what we can see right off the bat is that we're not quite capturing the undulations and the patterns within the data, but rather we have some sort of interesting looking spikes. It's getting some of the peaks, but certainly not all of them, and it's certainly losing a lot of the patterns. So the initial sort of impression is that this model is probably not performing all that well. Nonetheless, the model was used to forecast data, and the actual data points were stored in a separate data frame. Now, of course, before the forecast was done, there was another time series generated of 113 input length and 118 batch size. The input and output data, however, this time was a full data set, which included both the training and validation data. And the model was then retrained, this time on the forecast time series, with the same 10 epochs as the training data. And then finally, a for loop was utilized in Python to generate some forecasted values, which were then inverted to undo data normalization. They were assigned to a new data frame, and all in all, they were plotted next to the original data frame values side by side, as you can see here on your screen now. We have here the original data frame. This is all training data plus validation data, and then we have forecasted data. And then as a final evaluation step, the forecasted data was added to the same data frame as the actual data, and then plotted one over the other. Here's the forecasted data in green, and here's the actual data in blue. And what we can see is the forecast does not do a very good job. The model does not do a great job of forecasting. We see here what looks to be a very repetitive sine wave-like pattern. It's the same peaks and troughs, same amplitude. It's got a specific amplitude and frequency, and does nothing to capture the sort of spikes and the peaks and the undulations that we see within the actual time series data. So this model is not doing a great job of forecasting the data, and it does not perform very well, and certainly the model should be improved, and hopefully we can do that. But as a final numeric way of looking at how the model performed, I compared the forecast values to the actual values and computed an RMSE value, a root mean squared error value, of 9.9916. Now that's quite high. The lower the better, obviously. When I get close to 1 and actually 0, we're never going to get to 0, but we can certainly get below 9. And 9.9916 is very, very high, and certainly does not inspire confidence in this model. So as we move to part 5, we now know that there's quite a bit of redesigning we can do to this LSTM. So how do we do that? Well, we use the same data set, we use the same data split, 80-10-10. But what we do now is we change some of the parameters. We decrease the number of layers from 4 to 3. Why? My reasoning was the same as the reasoning for decreasing the number of neurons from 100 to 50 per layer, and that was to decrease model complexity. Because perhaps the model was so complex that the network wasn't fully able to learn, and just introducing complexity for the sake of it is not a good thing in data analytics, in my understanding at the very least. Now, accordingly, because the layers of LSTMs dropped from 4 to 3, the dropout layers dropped from 3 to 2, but I decreased the dropout percentage from 20% to 10% in the hopes that now we can retain more of the data and learn more of the pattern through the learning process. Perhaps 20% was too high of a rate, and that's why we didn't get a good understanding of the data in the validation set. I changed the length of the time series input from 100 from what it was before, 113 to 243. The reason I did that was I first thought, okay, this is hourly data. There's 24 hours in a day. I want to capture at least 10 days worth of data. Perhaps this will allow me to go over the span of missing data as well that I dropped out, and that would equate to 240 length. But I changed it to 243 to again allow for a nice even batch size based on the number of records that I was looking at. And that batch size was 139, and I increased the number of epochs for training to 20. Once again, hoping that allowing some more training would reduce error and bias and increase model performance. Now, this is just a quick look at the diagram. We lost a layer of LSTM, we lost a dropout layer, but the same function, the same sort of methodology applies. Here's how the model performed on its loss visualization after training. After 20 epochs, it certainly had quite a low loss value, and that's encouraging, but perhaps also signals some overfitting of data. Perhaps we've done too much. But when I did again the same process of generating some predictions on the test data, on the validation data, and laying it over the actual the actual data, the actual validation data plus training data, we see here the model's forecast here predictions are pretty good. They're certainly much better than the previous models. We see here quite a bit better understanding and capturing of the pattern. It looks to quite closely approximate some of the undulations. It doesn't go quite as far in the peaks and the troughs, but it's doing a better job here. Perhaps it's overfit, and that could be a concern, but it's still doing a good job. So it's encouraging as we now go into the forecasting process, which was done in the exact same way as before. A for loop was generated, a new time series was generated, a for loop for forecast predictions, and this is what the forecasted data looked like right after the training and validation data side by side. So it looks different from the previous one, but once again, when it's overlaid, we see that we have again that repetitive pattern. Now it seems to be closer to the original values, so it's doing a slightly better job of understanding perhaps where to start, but again it's missing out on all of this sort of pattern here that we're seeing, and it's just down here. It's not changing and modifying where those peaks and troughs are. Now that, of course, we have here an RMSE value that is still quite high of 8.7152, so this model too doesn't seem to be inspiring a whole lot of confidence and doesn't do a good job of forecasting some of the seasonality and irregularity of these temperature patterns. But as we move to part 6, we can now compare the two models. As I mentioned earlier, the second model does perform better than the first model, so that's a good sign. We have decreased the RMSE, and as we can see here with the forecast data, it seems now to get a bit closer to the data. It seems to have some higher peaks, but it doesn't change all that drastically, so neither model is really providing much confidence for forecasting. If we look at the model performance as it did on the validation data, look, the second model clearly does better than the first model. But as I mentioned earlier, and it's significantly better, perhaps we've just overfit the data. So we might have some slightly lower RMSE on the forecast data, but I still wouldn't think that that's a good reason to use either of these models for forecasting. In fact, I would suggest that neither of these models should be used, and much further fine-tuning needs to be done. But perhaps some of the reasons that I had that improvement in the second model is because I decreased some of the complexity, I dropped a layer of LSTMs, I decreased the number of neurons, and perhaps crucially, I increased the number of epochs from 10 to 20, and I decreased the dropout percentage from 20 to 10, so more information was retained. But all in all, throughout this project, through simple RNNs and LSTMs, I learned that designing neural networks is not simple or easy. It's in fact quite complex. There's a lot of complexity to grapple with, a lot of parameters to fine-tune and understand, including just the number of neurons to include within a layer. How many neurons should be in a simple RNN? How many in an LSTM? There's several things that need to be fine-tuned to allow for the models to perform as well as they can, to prevent underfitting, to avoid overfitting. There's a lot of complexity in there. And LSTM networks are even more complex than simple RNNs because of the fact that they have more hidden layers and there's more factors to consider. How many neurons within each layer, how many dropout layers, if any, what percentage to consider. All of these factors can play their part. And then, of course, is the fact that models take quite a bit of time to train. My LSTM models took between 10 and 20 minutes to train. That's a decent chunk of time. Sometimes they might even take up to 25 or 30, depending how complex your model is. So it would be good, very, very good, to understand how to tune those parameters just at the outset, so that we're not sitting by idly waiting for a long time to arrive at a model that turns out isn't of much help to us. Now, of course, every time we train a model, there is some learning to be gained. We should take some learning from it. We should adapt and fine-tune parameters, as always. But it would be good to be able to start in a better place than we did, at least with the first model that I trained, which certainly didn't do a good job at all, either on validation data or on forecasting data. But nonetheless, it's encouraging that I saw some improvements from my model in part 5 as compared to part 4. So at least I might be on the right track, and perhaps I have some platform as I continue forth dealing with RNNs, LSTMs, and machine learning in general. But all in all, I've been Huzaifa Siddiqui, and thank you so much for listening to my presentation, and I really look forward to seeing the videos that you guys have put out there and seeing how you've dealt with these neural networks. Thank you so much. Bye-bye.